All right, in section 4.4 of your book, we learn about this thing called the mean value theorem. And this section is kind of a weird section in that what we learn, we're never really going to use in this class. Really, this theorem doesn't come into play until, I guess, calculus 2, maybe? It'll end up being useful later on to prove some facts. But for our class, we're not really going to do anything with it. So that's kind of frustrating from the student's perspective. So I'm talking about it today, not because it's really important for calculus 1, but because any teacher will assume that you know the mean value theorem if you finish calculus 1. I don't know that's important enough to warrant an entire section in your book, but your book decides that it is, so here we are. Anyways, the mean value theorem. The first comment I want to make is if you just see it written, it sounds a lot more complicated than it is. There's a lot of kind of complicated vocabulary words and symbols going on in here, but when you get to the heart of it, it's not all that complex. Basically what it says is that if you have this function, and importantly the function is continuous, so we learned what that meant earlier in the class, and it's also differentiable. I don't think that's a word that I've defined yet. All that means is the derivative exists at every point in this interval. And maybe you're like, well, what do you mean? How could a derivative not exist? Well, one way it could not exist if your function was discontinuous, right? If I had a function that kind of did something like this, sure, that'll work. And then I asked you about the slope of the function at this x value right here, where I have this vertical asymptote and this jump discontinuity. You wouldn't really be able to answer my question, how steep the function is, right? And maybe you're like, yeah, okay, but do we really need this word differentiable because we already take care of this case when we talk about continuous? Is it possible for a function to be continuous and not differentiable? And the answer is yeah. It's entirely possible for the function to be continuous, but to not be able to find the derivative at some point. Remember, the derivative, we think about that as the steepness of the curve, but really it's the slope of the tangent line to the curve. And if my curve had like a sharp turn, kind of like this one does at this point right here, I couldn't talk about the slope of the tangent line at this point. Because remember, the way we define the slope of a tangent line at a given point is we choose that point as one of the 2 points that define the secant line, and then we choose some other point not equal to that, and then we let that second point get closer and closer to this first point. And if this second point gets closer and closer to this first point in this direction, my secant line kind of starts to look like this, so my tangent line would have a large negative slope. But if I do the same thing where one of the points defining the secant line is at this point and the other one is to the left, well, now as this point in purple approaches this other point in purple, my secant lines have slopes that are larger and larger positive numbers. So the limit from the right does not equal the limit from the left, so the two-sided limit is not defined. The point that I'm trying to make is if your curve has a sharp turn in it, like this green one did before I drew all over it, we can't talk about the derivative at that point. The most common example of a function that's continuous but not differentiable would be something like f of x equals the absolute value of x. The graph of this function is this v-shaped function, and it's perfectly fine to define the derivative over on the left, and to define the derivative over on the right. It's always -1 over here, it's always +1 over here. But at this point right here, at 0, at kind of the point of the v, the derivative is undefined because we can't talk about the slope of the tangent line at that point. Would it be -1? Would it be +1? Would it be some other number in between? I don't know. We can't agree. The derivative doesn't exist at this point. The function is not differentiable. You're like, whoa, that's a really weird case. We're getting into weird functions now? No. The mean value theorem is saying if we don't have a weird function, if our function is not discontinuous, if our function is not differentiable, the mean value theorem only applies for the functions that you're thinking of, the kind of normal functions that are continuous and are differentiable. Anyways, if our function satisfies this criteria on some interval from a to b, so I don't need the function to always be continuous or always be differentiable, but there does have to be some interval between two numbers where it satisfies this criteria, then the big takeaway of the mean value theorem is this statement right here. And maybe you're like, whoa, what in the world does this statement mean? I see a lot of symbols I don't quite understand. Well, informally, what it's saying is there has to be a point inside this interval where the instantaneous rate of change, think the derivative, at that point is equal to the average rate of change over the interval. And you're like, didn't understand it up here with all the math symbols, don't really understand it down here with your supposedly easier version of stuff. What's really going on? Okay, in my mind, the mean value theorem is a picture. Here's the picture. I have this function f of x, and I have this interval from a to b. If you really like numbers, maybe a is equal to 1 and b is equal to, 5. Sure. 1, 2, 3, 4. I guess that's nowhere near 5, 6, 7, 8. Let's call that 9 so it looks like it's a little bit more to scale. It really doesn't matter. I have this function right here, y equals f of x, and this interval from x equals 1 to x equals 9. And note that on this interval, this function pictured in blue is both continuous and differentiable. There's no discontinuities in here, and the curve is smooth, loosely speaking. There's no sharp turns anywhere in here. I don't know what the function looks like when x is greater than 9, right? Maybe it continues off this way, and maybe there's some, I don't know, discontinuity over here. Sure, no problem. Maybe there's even a point where it's not differentiable. That's all totally fine. I don't care what the function does when it's outside of this interval from 1 to 9. I'm only talking about the interval from 1 to 9. If I look at that interval from 1 to 9, what I can do is connect the starting point of that interval with the ending point of that interval and calculate the slope of that secant line. Assuming you really like numbers, let's suppose the y-coordinate right here is 2. And the y-coordinate way up here is, I don't know, maybe 10 to make the numbers work out nicely. So here's a 5 right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Close enough to scale. Anyways, if my function is continuous and differentiable on an interval, in this case the interval from 1 to 9, then there must be a point inside this interval. So a number, c, that's less than 9 and greater than 1. It has to exist. Some special point. What makes that point so special? The slope of the tangent line at that point is the exact same as the slope of the secant line connecting the start of the interval and the end of the interval. Really what this secant line represents is the average rate of change of this function f of x from x equals 1 to x equals 9, or more generally from x equals a to x equals b. To calculate the average rate of change, what I do is I take the difference in the two y-coordinates, so in this case f of 9 minus f of 1, or more generally f of b minus f of a, and divide that by the two x-coordinates, 9 and 1 in this example. As we saw earlier in this class, the average rate of change comes from this formula, which I can evaluate because I know f of 9. F of 9 is just the height of the function at this point, which appears to be 10 from my picture. F of 1 is the height of the function at this point, which appears to be 2 in my picture. The average rate of change is whatever I get when I do 10 minus 2, 8, and divide that by 9 minus 1, also 8. The average rate of change of this function from x equals 1 to x equals 9 is just equal to 1. In other words, the slope of this secant line right here is equal to 1. What the mean value theorem tells me is, because the curve is continuous and differentiable on this interval from 1 to 9, there has to be at least one magical point in here that they call c, so that the slope of the tangent line at that point is the exact same as the slope of the secant line. To write that more mathematically, I'd say f prime of c equals 1. The mean value theorem guarantees the existence of a c in between 1 and 9. In this specific case, there's more than one value that satisfy this criteria. There's a point, I don't know, somewhere over here, whatever this x-coordinate is, so that when I draw the tangent line right here, that tangent line has the exact same slope as this secant line. But the mean value theorem doesn't care that there's two of them. All the mean value theorem says is that there's got to be at least one of them. If f is a continuous real value function, meaning what comes out of this machine are just real numbers, which is all we've seen in our class, on the interval from a to b, so think 1 to 9 in this case, technically it's a closed interval, but you don't have to worry about it being closed versus open, and my function is differentiable on that interval from 1 to 9, no sharp turns between 1 and 9, technically you only need it to be an open interval, but again, don't worry about that. Where a is less than b, yeah, of course, the start of the interval has to be less than the end of the interval. Then there exists some c in this interval from a to b, such that f prime of c, think slope of the tangent line, is equal to this expression being exactly the average rate of change. That's all the mean value theorem says. When someone says mean value theorem, if you can picture this picture, it shows you understand it perfectly. Really what I'm tasked with doing in this video is not just telling you what the mean value theorem is, but kind of proving that it has to be true. And you might be able to kind of prove it to yourself just by kind of thinking about it. Like try to draw a curve that's continuous and differentiable that starts here and ends here that doesn't have a tangent line with a slope equal to the slope of the secant line, right? Maybe you start coming up here, but you're like, oh, I'm getting close. I got to avoid that, so I better turn it up this way. But there's a problem. You got to get back down to this point. And to get back down to this point, you're going to have to cross some threshold where the slope of the tangent line is equal to the secant line. That's a pretty weak proof to just kind of draw squiggly lines all over my curve. And I'll do better than that. But I want to make the point that this isn't some counterintuitive result. It makes a lot of sense that there must be some point between 1 and 9 so that the slope of the tangent line is equal to the slope of the secant line from 1 to 9. Really what the mean value theorem is it's a generalization of this other theorem called Rolle's theorem. And Rolle's theorem is very, very similar to the mean value theorem. It has the same criteria that we need to have a continuous real value function that's differentiable on some interval, like all that same legalese about our function must still be true. We got the same preamble. The only difference is with Rolle's theorem, we have one more stipulation. The height of the function at the start of the interval must be the exact same as the height of the function at the end of the interval. So I don't know what this height is right here, right? If you really want to see numbers in here, maybe a is equal to, I don't know, 2, 1, 2, 3, 4, 5. And maybe b is equal to, I guess, 14 in this quick little picture that I drew. I don't know what this height is right here. It kind of looks like it's 0 if this is the x-axis, but maybe really the x-axis lives down here. It doesn't matter what the height is of the function when x is equal to 2. The point is just that that height, whatever it is, has to be the exact same as the height of the function when x equals 14. And if you're in that case, where the height at the start of the interval is the same as the height at the end of the interval, then there must be some magical number c so that the slope of the tangent line to your curve is equal to 0. If the height of the function is the same at the start and the end, then there must be some point where the tangent line at that point would be horizontal. Maybe that's even easier to talk yourself into. Think about the behavior of the function, not necessarily the one pictured, but any function at the start of your interval at a right here. I mean, you kind of have three options, right? Either it starts out by going up, it starts out by going down, or it starts out kind of staying flat. If it starts out by staying flat, then the slope of the tangent line is equal to 0 immediately, and I'm done. I've satisfied the criteria that I need. If it starts out by going up, well, then eventually it's got to come back down because it starts and ends at the exact same height. And if it switches from going up to coming back down, there must be a point in between where it's flat. And you're like, well, not necessarily. I mean, I could have some really weird behavior where it's going up, 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 and then it stops and it jumps way down here like some Pac-Man style and ends up here. Okay, true. You can draw a weird function that never has a horizontal tangent line, but it'll be discontinuous. And remember, in the preamble to Rolle's theorem, much like the preamble to the mean value theorem, we're assuming that our function is continuous. So this is not a counterexample where it jumps from the top back down to the bottom. Nor is this a counterexample. You're like, technically, the slope of the tangent line never equals 0 for this curve in red because I have this kind of sharp turn at this point. And I'm like, yeah, that's true. But at this point, the curve is not differentiable. And in our preamble, it specifies that the curve has to be differentiable on this interval. And if you don't allow those two tricks, there's no way for a function that starts out by going up, loosely speaking, to get back down to the height that it started at by the end without having a horizontal tangent line. The only way a function can go from increasing to decreasing is if it's flat somewhere in between, assuming the function's continuous and differentiable. And the same logic works in reverse if the function starts out by going down. If the function starts out going down, eventually it's got to come back up if it's going to end up with a height that's the exact same at the start and the end. And if it's switching from decreasing to increasing, there must be some point in between where the function is flat. If you'll buy that argument for Rolle's theorem, that kind of a proof of Rolle's theorem, then the mean value theorem comes pretty easily. All you got to do to change Rolle's theorem into the mean value theorem is kind of tilt your head to the side a little bit, right? Take this entire graph right here and sort of rotate it a little bit this way so that A is still down here, but now this point B is somewhere up here, and so my curve looks more like this maybe. If I do that rotation, this point that used to be parallel with this axis is now parallel with the line connecting the starting point and the ending point, which is exactly the claim of the mean value theorem. That's not a proof of Rolle's theorem, nor is it a proof of the mean value theorem, but hopefully it's a good enough argument where you can kind of follow the logic. Your book contains a proof of these theorems, and it might be instructive for you to read, especially if you're going to go on further in calculus. But I kind of feel like as long as I've explained to you what the mean value theorem is and kind of made an argument for why it's true, I've sort of done my job. So maybe I'll call that good. Before I end this video, what I want to do is show you kind of the mean value theorem in action. So let's take a look at an example that's purely algebraic. Suppose we have this function y equals 3 over x plus 4. And we're considering the interval from x equals 1 to x equals 3. The first comment that I want to make is this function is both continuous and differentiable on this interval. It's worth noting that this function isn't continuous everywhere. If x equals 0, I have a vertical asymptote, and at that asymptote, it's discontinuous. But 0 is not within this interval. And remember, I don't really care what the function does when it's outside the interval in question. I only care about the function on the interval from x equals 1 to x equals 3. This function is both continuous and differentiable. What the mean value theorem tells me is that there must exist a value of c where c is some number between 1 and 3 so that f prime of c is equal to negative 1. Wait, where did that negative 1 come from? Consider the average rate of change of y equals 3 over x plus 4 from x equals 1 to x equals 3. My average rate of change formula is just the difference in the two y coordinates divided by the difference in the two x coordinates. In this case, the two x coordinates are 1 and 3. So my average rate of change is f of 3 minus f of 1 divided by 3 minus 1. F of 3 I can figure out by changing all the x's into 3's here. 3 divided by 3 is equal to 1, plus 4 more is equal to 5. F of 1 I can figure out in the same fashion, changing all the x's into 1's. 3 divided by 1 is 3, and 3 plus 4 equals 7. So I get 5 minus 7 divided by 3 minus 1. I get negative 2 divided by 2. I get negative 1. The slope of the secant line connecting the point on this curve at x equals 1 to the point on this curve where x equals 3 is negative 1. Because the slope of that secant line is negative 1, there must be a value of c in between 1 and 3 so that f prime of c, that's important that it says f prime in here, that's annoying that wasn't in there already, is equal to negative 1. That's what the mean value theorem tells me. It's an existence theorem. It doesn't tell me what c is, it just says there must exist a c between 1 and 3. What questions typically look like in the mean value theorem is what you see in front of you, where you're asked to figure out what c is. And fortunately, that's easy enough. If I call f of x 3 over x plus 4, I can figure out f prime of x by taking the derivative of 3 over x plus 4. Maybe I'd rewrite 3 over x as 3x to the negative 1 plus 4, so that's more conducive to my derivative rules. I pull the 3 out in front, and then the derivative of x to the negative 1 power is negative 1x to the negative 2 power, and the derivative of this 4 is just equal to 0 because it's a constant. What I get is that f prime of x is equal to negative 3x to the negative 2 power. This is the derivative at any value x. What I want to figure out is what value of x will make this derivative equal to the average rate of change, negative 1. That's easy enough. I just take negative 3x to the negative 2, set it equal to negative 1, and solve. To solve this, it might help to write the equation without negative exponents. So note that negative 3x to the negative 2 power is the same as negative 3 over x squared, and that equals negative 1. So to solve this for x squared, maybe I'd multiply the x squared up to the top right-hand side and get negative 3 equals negative x squared. If I multiply both sides by negative 1, I get 3 equals positive x squared. And if I take the square root of both sides of the equation, I get x equals plus or minus the square root of 3. What this is saying is there's two different x values for this function where the derivative of the function at those x values is equal to negative 1. It happens once when x is equal to the square root of 3, and it happens once when x is equal to the negative of the square root of 3. What the mean value theorem tells me is one of these solutions has to be between 1 and 3. The square root of 3 is roughly 1.4. Wait, no, that's not true. It's not 1.4. It's like 1.7 or so. But whatever, it really doesn't matter. Whether we call it 1.4 or close to 1.7, either way, it's in between 1 and 3, which is the claim that the mean value theorem makes. It's pretty easy to get lost in the algebra of what we're doing here. So in case it helps, here's a picture of what's going on. Here's my function, f of x equals 3 over x plus 4. Really what I did is I took the graph of 1 over x, which kind of looks like this, and I stretched it vertically by a factor of 3, and then I shifted it up 4 units, and that produced the graph that you see in front of you. Note that it's got a discontinuity when x equals 0. It's got that vertical asymptote, but I don't care at all about that. I'm really only considering this function from x equals 1 to x equals 3 on this little band right here. Note that on this band right here, my function is both continuous and differentiable. It's continuous, it never jumps anywhere, and it's differentiable, it doesn't have any sharp curves. To figure out the average slope of this curve on the interval, all I got to do is connect these 2 points. That's the line that you see in red right here. There's my secant line. The mean value theorem tells me there must be some x value in between 1 and 3 so that the slope of the tangent line is the exact same as the slope of the secant line. Look at this line in green. Can you tell that it's parallel to the line in red and therefore has the exact same slope? If so, good. Can you also tell that it's the tangent line to this curve at a point somewhere in here? I don't know exactly where. If so, good. If we look for the x-coordinate of this point, which remember is just kind of approximated on our graph here, it's some number in between 1 and 2. Maybe it's roughly 1.7. It's at the square root of 3. The slope of the tangent line to this curve, pictured in green, at the square root of 3, which note is in between 1 and 3, is the exact same as the slope of the secant line to this curve from 1 to 3. That's what the mean value theorem is telling me. Typical problem in the mean value theorem looks like this. It's a little bit more algebraic. And if you can tie this together with the graph, you understand the mean value theorem perfectly.